The next presentation is by Volker Rummenhohl, and he asked me to mention that he has just had a jaw surgery fairly recently, so be patient. He's going to try to articulate as well as he can. I personally understood him quite well, so we're looking forward to hearing from him. He's the Vice President of Catalyst Technologies, Fuel Tech Incorporated, and he'll be talking about some advancements in selective catalytic reduction for NOx control. Welcome.
Thank you very much, Frank. And good afternoon, ladies and gentlemen. I'm very pleased being here today, having the opportunity of presenting this. This presentation will be totally different from what you heard this morning or yesterday. It'll be pure technology, and there will be no politics involved. So.
Good.
The presentation is about the technology if you happen to have a coal-fired unit and still have to reduce NOx further. We are looking at a lower capital cost solution for that, and we call that advanced selective catalytic reduction. What I will talk about in a short introduction, after a short introduction about one of our ASCR projects in Taiwan, and field results from this unit. In the introduction, very quickly to Fuel Tech. Fuel Tech is a company engaged in the innovation. Fuel Tech's air pollution control business started with the original license from Mercury for SCR, and over the years, Fuel Tech has developed all kinds of NOx reduction technologies. This is a chart I almost could have skipped. We have heard this in every presentation. On one hand, for coal units, the emission standards are still getting more stringent, but with the abundance of natural gas, those units are not anymore base-loaded. With that, it becomes more important to get low capital cost and maybe a little bit higher O&M cost solutions. With that solution general to the ASCR technology, the ASCR technology combines several NOx reduction technologies like low NOx burners, overfire air, SCR, and once you have done that, you need much less catalyst, and that really reduces the cost compared to full-scale SCR, which certainly is the best available control technology for NOx reduction. But with those solutions, you get into the same range of NOx reduction with significantly reduced capital cost. That brings me to this example. It's an 80 megawatt T-fired unit located in Kaohsiung, Taiwan. And it burns multiple fuels, Adaro coal, coke oven gas, and blast furnace gas. The plant needed to reduce NOx by more than 78% from a baseline of 230 ppm to below 50 ppm. The unit already had existing low NOx burners of the first generation and an existing SCR system. What was added now, new low NOx burners, state-of-the-art burners, a new overfire air system, and an improved SCR system, and one small reactor with catalyst between the economizer and air heater. It's a single layer of catalyst with only 12 modules of plate catalyst. If we compare that, and it was really a good comparison in this case because we were competing against a company offering pure SCR. The ASCR, the catalyst, has to reduce only just under 30% of NOx, whereas the standalone SCR would reduce more than 78%. With that, it would use 3 times the catalyst volume and about 4 times the construction footprint. The capital cost for those turned out to be for the ASCR roughly $5 million, for the SCR 10 million. So it's a 50% reduction in capital cost. This shows you, and I realize it's not very well to see, but the key point is on the left side we see a urea tank that goes to the distribution modules, and it distributes it to 3 different injection areas for the SNCR, but also to a forced level at the top of the boiler that feeds the catalyst. There were several design challenges. One of the things is we have 3 proven technologies, but bringing them together is a challenge. In the combustion, if you are not meeting your CO or not meeting your NOx, you have problems in the SNCR. Elevated CO leads to lower NOx reduction. Higher NOx coming from the low NOx burners also removes NOx reduction. And ultimately, the catalyst has to do the rest. If the outlet of the SNCR is not according to design, the SCR will not provide the final result. Furthermore, besides the absolute values, an SNCR system usually provides a very inhomogeneous ammonia to NOx profile. So this has to be evened out before we get to the catalyst. The number one thing with doing that is flow modeling. Flow modeling, as you see on this slide, with CFD, computational fluid dynamics, and we also did a physical experimental modeling, and we used this technology to really make sure that we come to the catalyst with a very even ammonia to NOx profile. You can see on the top, the red are the areas of very high NOx, and it gets a little bit reduced through the economizer. But then we have installed a mixer, and you see the final result at the catalyst is what we need. One of the things that made this technology possible, and I will at the very end talk about other units bigger size, is this what we call a graduated straightening grid. You can see at the inlet of the reactor, it's a series of blades which turns the flue gas absolutely evenly into the catalyst. What this allows us is to increase the velocity through the catalyst. The design for this example is 20 feet per second. The other example I have is 25 feet per second. If you ask around in the industry, people will tell you on coal units you cannot go higher than 15 to 18 feet per second. So this is really the core that made the technology possible. You can see here our experimental modeling. We see on the right side the ash hoppers. Very important for any type of catalyst is that we install an ash screen to take out large particles. On the left side is a drawing for the new low NOx burners. On the right side for the overfire air system. And those are a few pictures that demonstrate really the advantage of this technology. On the left picture, you see the unit before we started working on it, and you see the flue gas duct coming from the economizer to the air heater. On the right-hand side, you see how little we had to change to accommodate the catalyst. There is no steel going to the ground, so that's where all the savings come from. This shows you the catalyst loading with this extremely confined space. It was very difficult to do this, but we can load the catalyst, you can see on the left side, through three different rows at a time. So when we did the first time, the catalyst was loaded in 2 days. This shows you a three-dimensional CAD model, the border, SCR reactor, air heater, and precip inlet. I put this slide into the presentation to show you that we are saving a lot of money with having only one layer of catalyst. But on the other side, we have everything that is in every regular SCR system. We have a mixer that mixes ammonia to NOx. We have an LPA screen, straightening vanes, our GSG that I mentioned before, and we have installed one sonic horn for online cleaning. The catalyst we used in this case was plate-type catalyst with a 5.6 millimeter pitch and 0.8 millimeter wall thickness. The total volume installed was 25.3 cubic meters. That brings me to the last part of the presentation, and those are the results. In the performance test, we achieved 48 ppm of NOx, 50 was the guarantee. We achieved 4.3 ppm of ammonia slip, 8 ppm was the guarantee, and we passed both performance tests that was at full load coal. The next guarantee point was at full load, but a mixture of coke oven gas and coal, and you see the results are almost identical. On low load, the results were even better, and that's no wonder because we have relatively more catalyst available than at full load. And we achieved 45 and 3 ppm. The next project with this technology is on the same sites. What I showed you was Unit 7. We have started the design for Unit 6, and we will start the design for Unit 8 early next year. The inlet data are the same, but this time the client wants 30 ppm outlet NOx. That's why we have to install 2 layers of catalyst. And with that, I just want, this was a small unit, 80 megawatt, but we have done design together with an OEM, 4 units of this type, 685 megawatt each, located in Hong Kong, and they are in operation for almost 2 years. There we saved about 60% of the investment, and if you take 4 times 680 megawatt times $250 a kilowatt, you get somewhere 500–600 million. Saving 60% of that is quite a number. And that brings me to the conclusion of my presentation, and if there are any questions, I'll be happy to answer.
One of the things that's happening in today's world because of the various regulations is that we're asking a lot more out of our SCRs than it used to be. In addition to low ammonia slip, we're asking for very low SO3 generation and also for mercury oxidation. Have you looked at those?
Yes, I mean, we are offering this ASCR, but also SCR technologies, and the Mercury Oxidation, we had one plant on the East Coast with 1 layer of catalyst. It had more than 80% oxidation of mercury. The next unit, 2 units in Taiwan, will be for lower ammonia slip. And the SO3 is in almost every single project, one of the critical items. And we are working with all the catalyst suppliers to come up with the lowest possible rate.
Other questions?
Hi. Does increasing the velocity of the gas up to 25 feet per second increase the risk of the erosion of the catalyst at all?
Generally, it certainly increases it. It increases it almost to the power of 4. But the fact of this GSG is not only the equal distribution of velocity. The main thing is that it goes absolutely parallel into the catalyst. And the 4 big units I talked about, the first of those 4 units is already 2 years in operation, and there were no signs of any kind of erosion.
Question there?
Does your device require ammonium makeup?
Sorry?
Do you need the ammonia makeup for the 3% slip?
No.
Other questions? Thank you very much.
Thank you.